Okay, so on Wednesday we introduced the approach to solving for traveling wave solutions in nonlinear partial differential equations. And essentially what we said is that if you have some PDE, that's some nonlinear function of the time derivative of the PDE is some nonlinear function of the unknown function and its derivatives and potentially higher order derivatives. The approach to obtain a traveling wave solution is to assume that along some traveling wave coordinate, you have solutions of the form u of xt equals v of xi, where xi is equal to x minus ct. And then we use a phase plane approach to analyze the solutions to the resulting nonlinear ODEs. So in the case where we introduce viscosity to Berger's equation, we have the following nonlinear PDE I'll write it like this: du dt equals u times du dx. Sorry, du plus u times du dx is equal to epsilon d2u dx squared. And so if we look for traveling wave solutions, in this case, specifically ones where our traveling wave coordinate is given by x minus st over epsilon, and then we're going to have solutions of the form u equals v of xi. And in the case of Berger's equation, right, remember that we're going to assume that we have traveling front type solutions, okay? Because remember in Ingus-Berger's equation, essentially what we had was u sub t plus ux equals 0. We had solutions that propagated like this, ever steepening until we got a shock here, okay? But they traveled like traveling fronts in this case, where essentially the back of the front is at one level, v plus, and the front of the front is at another level, v plus. Sorry, v minus v plus, okay? Now, we could have a receding front, in which case v plus would be higher than v minus. So we have to explore both of those possibilities, right? The boundary conditions in this case are going to be given by the limit as xi goes to plus or minus infinity, v of xi, the limit as xi goes to plus or minus infinity, v prime of xi. This is equal to 0. So this is equal to plus and minus v, and v prime is going to be equal to 0. Okay. So that's our set of boundaries, right? How do we get our resulting ODE? Well, we're just going to plug in the ansatz into the PDE, okay? So if I assume that v of xi is equal to u, xi is equal to x minus st over epsilon, and if I have u sub t plus ux is equal to epsilon u sub xx, right? Then I need to compute all the component parts, right? So du dt, let's do it piece by piece, is going to be equal to what? Well, it's going to be equal to dxi dt t multiplied by dv dxi, which is just v prime. Dxi dt in this case is going to be equal to minus s over epsilon. And so that multiplies our v prime. U times u sub x is just going to be equal to v multiplied by dxi dx dv dxi, which is equal to v multiplied by 1 over epsilon times v prime, or 1 over epsilon v prime. Lastly, u sub xx, right, is going to be equal to dx of dxi dx dv dxi, right? So we're going to end up with a 1 over epsilon squared times v prime prime. Okay. Now, our resulting ODE then is going to be minus s over epsilon v prime plus v 1 over epsilon v prime minus is equal to epsilon times 1 over epsilon squared. So I just get a 1 over epsilon v prime prime. And now you see why we incorporated this additional scaling factor of epsilon, because all these epsilons now will vanish if we multiply through by epsilon. Okay, so we can rearrange this a bit. All right, so we get v prime prime is equal to v prime minus s v prime. Okay, if we integrate this by psi, well, this term will become v prime. This term here will become v squared over 2. And this term here will just become minus sv. And then we'll have an additional constant term here. Okay. So far, right, our c and s are going to be free parameters. Okay. So just think about, well, how do we specify those free parameters? We need to apply our boundary conditions, right? So to start with, let's take the limit as psi goes to plus or minus infinity. Okay. In that case, this term here would go to 0. Right? So we get a 0 on the left-hand side. What about this here? Well, it can either be v plus or v minus. Okay. And this here can either be v plus or minus. And the c just goes along for the ride. Okay. So I can actually specify c now in terms of everything else. I get c equals sv plus or minus v plus minus squared divided by 2. Okay. And so I can set c to be either thing. Okay. Let's just start by setting c equal to the minus version of that, right? So since c is free, okay, just set C equal to SV minus V minus squared divided by 2. You could set it to B plus and see what happens, okay? And we would get sort of the mirror image of the equation that I'm gonna show you, right? So if I plug this in now, right, we get SV minus V minus squared divided by 2 is equal to SV plus minus V plus squared divided by 2, okay? So if I had taken, this side to be V plus, this would just cancel out. If I had taken this side to be, V plus, then I would take the right-hand side to be V minus in this case, okay? So working this out, okay, we can rearrange it as S times V plus minus V minus, okay, and just moving this over here is equal to V plus squared minus V minus squared over 2. But of course, we can divide through by this. We can, factor out the factor of V plus minus V minus, and we just get the average of V plus and V minus, okay? So what that means is if we return to the original equation, now what we have is V prime is equal to what? Well, let's go back here, right? Here's our equation, right? I can plug in for S and C now, and I end up with a half V squared, right? Minus S V plus now, and then what did we have for C? This term here, okay? So we had SV minus V minus squared over 2. So if I rearrange things, right, I can write this as V squared minus V minus squared over 2 minus S times V minus V minus, okay? And so we note that V is just equivalent to V minus solves the ODE if V plus is equal to V minus, okay? But this is not a traveling wave solution, okay? Which we want a traveling wave solution, okay? Now, in your homework, you're actually going to derive the traveling wave solution by finishing this analysis. And essentially, that requires that V plus be less than S, which is equal to V plus V minus over 2, which is less than V minus, okay? Now, in order to show that, what you're going to have to do is essentially, set conditions on when this ordinary differential equation is going to have a non-trivial solution and when it's going to flow in the correct direction, okay? And the trick really is that you need V prime to be the correct sign, okay? So that V basically decreases from minus infinity to plus infinity, okay? So in other words, V prime is going to be less than 0. So if you look at this, right, whenever psi is very negative, right, you're going to need that whatever this value is, right, should be less than v minus squared, and s should be such that this whole right-hand side is always negative, okay? So in that way, you'll get a traveling wave solution that looks like this. Starts at a high value, goes to a low value, and also you have a traveling wave speed that is positive.